All right, so in this video, what we're going to look at is the other end of applications of exponential curves, and that's exponential decay. So for exponential decay, I've said here it's the obverse of exponential growth. It seems actually very impressive at the beginning because the decay rate is incredibly large at the beginning, but the decay rate decreases as the input grows. Eventually, the function will seem to level out or stabilize after a certain point. Again, you'll learn in calculus it's because the growth rate is proportional to itself. The growth rate of exponential decay is also proportional to itself, which is precisely the reason we get this asymptotic leveling out. So for a function that models exponential decay, we begin at large values, right? We begin at large values, and we decrease really, really fast, right? So let's actually start at a different point here. So we begin at large values, but we decrease really, really fast, and then as the output values decrease, the decay rate will also decrease, and so the growth rate will also shrink. And when we start getting small output values here, our rate of decay is also correspondingly small. And so we'll see this sort of leveling out behavior here. And so this would be an exponential decay curve here. And again, we can see this asymptote, and this asymptote would be at if it's just of the form y equals c to the x, then this asymptote would be at y equals 0. Then let's look at a specific example of exponential decay. There are many of them, but one of the most commonly used ones is half-life, which comes about in chemistry, physics, biology. Half-life is a very important concept. So in physics and chemistry, typically the application that's looked at is in matter. So matter doesn't live forever. There's something called radioactive decay that occurs in all atoms and subatomic particles like protons. So even protons decay. It's just on the order of many billions of years. So half-life describes the amount of time that a chunk of a particular substance takes to decay into half of its original mass. So let's say you have a block of some substance. Let's say you have just some sort of cube of some substance, and this substance is, I don't know, something that is radioactive, some sort of isotope of uranium that is radioactive. I can't remember which ones are more or the most radioactive, but let's say this is a very highly radioactive isotope of uranium. And let's say it is initially 1 kilogram in mass. Eventually, if you just leave it alone, if you just leave this block of uranium alone, eventually it will shrink because it is decaying, right? The atoms in here are shooting off alpha particles, beta particles, gamma particles, and eventually the mass will be smaller, and eventually, over a certain amount of time, it'll be a half kilogram, right? It started first as 1 full kilogram, and if you leave it for a certain amount of time, then it will eventually only be a half kilogram in mass, and that's why we call this the half-life. The half-life is the amount of time it takes for an object to be reduced to half its mass, its original mass. So how long did this take? Some time, we could call it big T, right? It's a very important amount of time, so we're going to give it a capital letter big T. This would be the amount of time it takes for this block of uranium to be reduced to half of its original mass. We would call this big time, this amount of time, the half-life. How long does it take for it to be reduced to half? So some atoms are very stable and thus take a very long time to decay in half their original mass. Uranium-238, for example, has a half-life of 4.5 billion years, which is around the current age of the Earth. Some atoms, however, are very unstable and don't take very long at all to decay into half their original mass. So another isotope of uranium, uranium-239, is incredibly unstable and has a half-life of around only 23.5 minutes. So the half-life of, let's say, U-239, the half-life of uranium-239 would be around 23.5 minutes. That would be the half-life. And the half-life of this much more stable isotope of uranium is much longer, 4.5 billion years. Okay, so that's what half-life is in a nutshell. Now, we're going to look in the next video at a formula that works to model both exponential growth and exponential decay, and we will apply it to an exponential decay problem for the half-life of some strange new substance. And we'll see you then.